very good day to our discrete mathematics lecturer PUAN SITI NORSHAFINAZ MOHD. Today we are going to present our case study. So today me and my teammates will present this case study to you. First of all, let me introduce myself. My name is ARVIND ULAKANATHAN, matrix number 01 DDT21F2071. Then my teammates PAULRAJ THAVARAJ and GHAVINDCHARAN and SUTHAGAR. So contents of our case study is 1.0 Introduction of Minimal Spanning Tree. Then the second is Technique Applied. Third is Solution. Include the diagram tree obtained and calculation. 4.0 Conclusion. The importance of minimal spanning tree. Introduction of minimal spanning tree. So what is minimal spanning tree? Minimal spanning tree (MST) is a subset of the edges of a connected, edges-weighted undirected graph that connects all the vertices together without any cycles and the minimum possible total weight, edge weight. This is why it is a spanning tree whose sum of edge weighs as small as possible. As you can see the pictures here. Minimal spanning tree. Problem. Select edges in a connected and undirected graph to form a tree that connects all the vertices. Spanning tree. Minimize the total edge weight of the spanning tree. So, as you can see, it is now total weight of this graph is more. So, minimal spanning tree is that you need to reduce the weight of the edges. So, as you can see, you take the least number or the small number of edges and then you total it, you will get total weight of 3 edges equals to 40.
Thank you, Arvind. My name is PAULRAJ, unlike THAVARAJ. My matrix number is 01 DDT21F1152. So now I will continue this presentation. Let us see the second point, which is technique applied. We decided to use the Prim's algorithm in our case study. Prim's algorithm basically is a greedy algorithm that finds the shortest path through a weighted graph. This means that it identifies a subset of the edges that form a tree that includes every vertex and where the total weight of all the edges in the tree is minimized. So, referring to the picture that I have attached in this slide, we can conclude that Prim's algorithm is all about find all the edges that connect the tree to the new vertices and find the minimum and add it to the tree. So this is basically a trick to Prim's algorithm. So in the example, there are 6 vertices and 9 edges. So after we use the Prim's algorithm, there are total of the 6 vertices and there are only 5 edges only. So basically how we use Prim's algorithm is from vertices 0, there are 2 edges going through. So we have to choose the shortest weight. So basically from 0, the shortest weight edge will be the 1. Then from vertices 1, there are 3 edges going through. So the less weight will be the middle one, which contain the 2. Then it will go to the vertices 3. So from vertices 3 there are 3 total of 4 edges, but the shortest will be 3. Then it will go to the second edge, but after that we cannot continue because it will build a shape. So we have to go back to the edge number 3. So the shortest will be 4. Then we will reach vertices number 4. So from vertices 4 we have to use the edge contain 5. Then we will reach at the final vertex, which is vertex 5. So this is how we build a graph, use the Prim's algorithm. Now let us see the third point, solution. In solution, we will see include diagram tree obtained. So our team have choose map 4 and then calculation.
Let us see the solution using Prim's algorithm for map 4. The question asked us to start from city center. So from city center, there are a total of 6 vertices that we can go through. So basically, using Prim's algorithm, we have to see which edge contains the less weight. So from city center, there are government house which contain 2.4 km, and then to Olympic Park 1.2 km, to Yara Park 1.5 km, then to RBG Royal Botanical Gardens 2.5 km, and then Flagstaff Gardens 1.5 km and Melbourne Museum 3 km. So the less weight will be the 1.2 km going to the Olympic Park. So I choose this edge and I use the highlight to so we can see easily. So we arrived at the Olympic Park. So from Olympic Park there are only two edges that we can go to, which is to Government House, which contains 2.5 km, and to Yara Park 1 km. So basically for sure I will choose the 1 km because it is more less weight. Okay, we have arrived at Yara Park. So from Yara Park there are three edges that we can go, which is to City Centre back again, or to Flagstaff Gardens, or RBG. So City Centre is 1.5, Flagstaff 3 km, and 1.4 will be RBG. So basically we have to choose the less weight, and if we choose the City Centre, it will build a shape, so it is totally wrong. So we have to choose the less weight, and we can't build a shape in this case. So I choose this edge which going to the RBG. So we have arrived at the RBG. So basically from RBG again we can go to the City Centre, but as I said earlier, we cannot do it because it will build a shape. So then the second edge will going to the Flagstaff Garden, which contains 1.9 km. Then the third edge, which is contain 2 km. So basically the last will be the 1.9 km going to Flagstaff Garden. So we have arrived at the Flagstaff Garden. So again from Flagstaff Garden there are total of 1, 2, 3, 4 edges, but as we use this path, so we cannot again return back to RBG. So the less is again 1.5 km to City Centre, but again and again we cannot use it because it will build a shape. So the second less weight, which will be the 1.8 km, which is going to the King's Domain. So I choose this edge. Okay, done. So now we have arrived at the King's Domain. So from King's Domain we can go to the Royal Exhibition Buildings or to Royal Botanical Gardens. So Royal Botanical Gardens is basically 2 km and REB will be 1.6 km. So I choose this as it is a more less weight. Okay, so we have arrived at REB. So after this, from REB there are two edges that we can use, which is to Fitzroy Gardens, which contains 1.7 km, and the second one will be the Melbourne Museum, which contains 2.2 km. So the less will be 1.7, so I'll choose to Fitzroy Gardens. So from Fitzroy Gardens we can go back again to Flagstaff Gardens, but it contains 2.3 km. So rather to use this path, I returning back again to REB. From REB I choose to Melbourne Museum, because if I return back to Flagstaff Gardens, it will create a shape, it will build a shape. So then if I return back to REB and then I choose to the Melbourne Museum, it contains more less weight and again it won't build a shape. So I choose this path. So from REB I choose Melbourne Museum. Okay, we have arrived at the Melbourne Museum. So from this there are two edges that we can use, which is to City Centre 3 km or to the Government House, which is 2.2 km. So for sure I will choose 2.2 km because we have to go through all vertices. So I choose the last one will be 2.2 km. So the last destination that we arrived is at the Government House. So this will be the solution for map 4, because we already go through all the vertices and we have been we go through all vertices and we have used the less weighted edges. So that's all for the solution. So the next slide will be the final output of this graph.
This graph will be the final output for map 4. As we can see, we drew this graph referring to the map 4 that we drew before this, and this graph will also help us to our next step, which is the calculation part, and the calculation part will be explained by GHAVINDCHARAN. So that's all from me. Thank you.
Thank you, Peter. My name is GHAVINDCHARAN, son of SUTHAGAR, and my matrix number is 01 DDT21F2060. Now I'm going to explain about the calculation of Prim's algorithm of table for this map. So how do we calculate? So we will find the shortest distance from the starting point. Okay, so the first one is from city center to Olympic Park, which is the weight is 1.2 km. Then the second one is Olympic Park to Yara Park, the weight is 1.0 km. And the third one is Yara Park to Royal Botanical Garden, which is 1.4 km. And the fourth one is Royal Botanical Gardens to Flagstaff Garden, which is 1.9 km. And the fifth one is Flagstaff Gardens to King's Domain, which is 1.8 km. And then King's Domain to Royal Exhibition Buildings, which is 1.6 km. Then Royal Exhibition Buildings to Fitzroy Gardens, which is 1.7 km. Then Royal Exhibition Buildings to Melbourne Museum, which is 2.2 km. And the last one is Melbourne Museum to Government House, which is the total weight is 15 km. Going to explain you about the importance of minimal spinning tree. So for example, for network architectures, minimal spinning tree are used. They are also used to come up with approximation for complicated mathematical problems like traveling salesman problem. The most common error is expecting the determining the shortest distance between the source and each of the points will give the correct solution. For practical purposes, replace the thread with the network and the points with routers. You will determine the quickest path for sending data across a specific collection of routers. As a result, scholars have focused their attention on the problem, and several algorithms are proposed to address it. That is all. Thank you.